So, any transition in finite automata which is written as this S1 on input symbol A going to S2. So, this is a transition. So, this transition is read as in state S1 on input A go to state S2. So, this is the meaning of this particular symbol S1 arrow with a label A to S2. So, this is read as this. If you go, if you find, if you are at the end of the input, so this was the whole input stream as I was telling. Now, if it is, so if you have reached the end of the input, so this point no more input is there, then we see whether the state at which the automata is at that point of time is an accepting state or not. So, if it is an accepting state, then the decision is accept, otherwise the decision is reject, and the accepting states are the final states, and they are identified by this particular notation, the states that will have two concentric circles in it. So, they are the accepting states or final state. So, that is the that may be the. So, if you are at this type of at any of this type of state, in that case, so it is accepted. However, if there is no transition possible at some for some state, like maybe at present I am at state say S 5, and S 5 the transitions are defined only on the symbols A and B to say this is say to S 7, this is to say S 9 like that. Now, so if the next input symbol coming does not match with either A or B, then from S 5 the system is unable to go anywhere, the or no transition is possible, and that, and in that case, so it will be a reject set. So, it will go to a reject. So, the input stream is not accepted as per that regular definition. So, it may so happen that some other regular definition will match. So, conceptually you can think that as if all the regular definitions are being matched parallelly by the lexicon analysis tool, and whichever rule gives the maximum match. So, that is returned as the token. At the final state of it, the token the matched token for that is returned to the parser. So, this is the way this operates, the finite automata thing. So, these are some of the notations, like a state will be represented by a circle or ellipse, whatever you do, both are same. The start state will have an arrow pointing to it. So, that will identify a start state, and accepting state will have two concentric circles or concentric ellipses, and a transition will be labeled from one state to another with a corresponding label A. Okay. So, this is it. So, these are the notations that are used for defining a state transition graph. So, this is one simple example, a finite automata that accepts only 1. So, this is the start state. So, we have got this this is the start state, and on getting the input 1, it comes to a final state. So, if you are giving as an input, if you give a single one, then it will come here, but if you give anything else, for example, if you give 0, then from the start state there is no definition, no transition defined with label 0. So, it cannot do a transition. So, it remains in this state only, and that is an error. Similarly, if you are final state, then suppose I have given 2 ones. So, on first one it comes to this state, but it does not know what to do on the second one. As a result, that is also an error. So, when the input is exhausted, so and you are if you are at an accepting state, then it is fine. If you are at some intermediary point, so if you do not know where to go, transitions are not available for for the current state. So, in that case it is a reject. So, a finite automaton accepts a string if we can follow transitions labeled with the characters in the string from the start to some accepting state. So, if it can lead you to some accepting state, then only the string is accepted. Some other example, like a finite automata accepting any number of 1s followed by a 0, single 0. So, all these strings are acceptable, like I can have say 1 1 0, I can have say 1 1 0, so similarly 1 1 1 1 1, any number of 1s followed by a 0, but this is not accepted. 1 0 1 1 is not accepted because it is not ending with a 0. So, in as far as this language is concerned, the alphabet set consists of the symbols 0 and 1. Now, the transition the finite automata is defined like this, that this is the start state. From the start state, as long as it gets 1, it remains in the start state. If it gets a 0, it comes to a final state. So, that way it is doing the transitions. So, in this case, so this 1110 is a valid string, but 110, if there is any more character, so that is not a valid string for this language, because once on a 0 it comes here, from this state no transition is defined, or neither on 0 nor on 1. So, as a result, the second one is not a valid string for the language. So, this way we can use this lexical this finite automata for representing the regular expressions. What about this particular example? So, you see that the string as long as it so you start at this point, as long as you get 1, you stay in the start state only. Now, if you get a 0, it comes to this state, and then if you get a 1, it immediately goes back to this state, the start state. So, it can reach final state only when there are 2 zeros, okay, 1 0 2 0, and then it remains there as long as there are zeros. Whenever it gets a 1, it comes back to the first state. So, some typical language that are accepted by this are say 0 0 0, or simply 2 zeros, first 0 second first 0 and second 0, it comes to this state, or 0 0 and on 0 it remains here. So, 0 0 0, or it may be any number of 1s, then 2 zeros. So, that is also fine. So, wherever it gets a 1 1 1 1 1, then 0, then again 1. So, whenever it gets a 1, it comes back to the first state, and to come to the end, the last state, it must have at least 2 zeros at the end. So, to summarize, I can say it is all strings terminated by at least 2 zeros. Okay. So, this particular finite automata, it corresponds to all the strings that are terminated by at least 2 zeros. Then because whenever it is getting a 1, it is coming back to the initial state. So, from that point it is again starting. So, then it can you can see that it will not be able to go to the accepting state until it gets 2 successive zeros at the end, and there is no more character. So, that way it will do this thing. So, given such finite automata, so you can trace it and find out the corresponding language, and you can try to write down the corresponding regular expression also. Like here, so I have to write the regular expression. So, it can be in the state 1 star, then it is any other string over 0 or 1 star, any number of zeros and ones, but then there has to be 2 zeros at the end. Okay. In fact, this 1 star is not necessary. So, you can forget about this 1 star also. So, this can be simplified as 0 or 1 star followed by 2 zeros. So, so if it gets 2 zeros, so it will come there, otherwise it will not. So, you can also try to from this regular expression, so you can try to draw the automata. So, this it has to, if it starts at a particular state, this is the initial state, then getting 1 0, it comes to this state, getting another 0, it comes to this state. I am trying to derive this automata from this regular expression. So, for 2 zeros it comes here. Now, there can be any number of zeros after this. So, I should say, so this is also not correct. So, there should be a 0 star at the end. So, as long as there are zeros, so it will remain there, but if it is similarly, as long as there are ones, so it will remain here. So, if it gets a 1, it will come back to this point, if it gets a 1, it will come back to this point. So, this way you can draw the corresponding. So, this is a derivation. So, ultimately you see that we have come to the same diagram as we have it here. So, from the regular definition you can come to the finite automata, or from the finite automata you can come back to the regular expression. So, both of them can be done. What about this one? So, you see that alphabet is say still 0 and 1. So, it says that as long as you get 1 you remain this state, and then on getting a single 1 you come to this state. So, the valid strings, if we try to enumerate, 1 is a valid string, but say 1 1, is it a valid string? Like on the first one it remains here, the second one it goes there. So, that is possible. Then so, then there were 3 ones. So, that is also possible, because 2 ones it will revolve here, and the third one it will come here. Of course, there is a problem in this particular case, as you can see that on 1. So, I can go to this state or I can remain in this state. So, there are two transitions, two possible transitions that are there corresponding to the symbol 1 at the start state. So, this is there is some sort of non-determinism. So, apparently it seems that this is not correct, but as such so we will see that this defines a new type of finite automata, which is known as non-deterministic finite automata, where there may be multiple transitions that are possible from one state based on the same input symbol, and if any of those transitions can lead me to a final state, final accepting state, then we are happy. So, we can do this thing. So, we will come to that as we proceed. Now, the operation of this automata is not completely defined by the input. So, because we have to take some non-deterministic decision, like at this point on getting 1 whether we remain here or we go from here to here. So, there is a decision, and that decision is not depicted by the finite automata completely. Whereas, in the previous example, so here there is no non-determinism, like at every point. So, if there are two transitions going out from a state, so they are labeled differently. So, on 0 you go here, on 1 you come here. So, this is deterministic, but here we have got non-determinism. So, the operation is not completely defined by the input. Another thing that we have is something called epsilon moves. Sometimes from state A to state B we may have a transition whose label is epsilon. So, epsilon means it will no input symbol will be consumed for doing a transition from A to B. The machine simply transits from A to B, but does not consume any input. So, machine can move from state A to state B without reading the input. So, if we have these two things in our hand, that is epsilon moves and this non-determinism, so non-deterministic decision. So, they will be constituting a different type of automata, which is known as non-deterministic automata or NFA. So, right now we can see that this finite automata, it can be divided into two classes. So, this finite automata, so this is called finite because number of states that we have in it is finite in nature. Now, this finite automata, there are two different types, one is deterministic, another is non-deterministic. So, there are two different types of finite automata. So, in a deterministic finite automata, so that we have seen at the beginning. So, there is one transition per input per state. So, from every state on some input symbol, there is a single transition that is defined. So, it will not happen that from a particular state I will have two different transitions and going to two different states and labeled with the same input symbol. So, this will never happen for a deterministic finite automata, and also there is no epsilon moves. So, there is no transition whose label is epsilon. On the other hand, this non-deterministic finite automata, so I can have multiple transitions. So, this is possible. So, from one particular state on getting the same input symbol, so it can go to two different states. So, now while doing the operation, it will non-deterministically select any of those two states and make a transition there. So, can have multiple transition for one input in a given state, and also can have epsilon movements, epsilon moves can also be there. So, this defines the non-deterministic finite automata or NFA. finite automata have finite memory because it needs only to encode the current state. So, only the current state has to be remembered. So, it can forget what that how did it reach that particular state. Like if this is the start state and at present you are in this particular state. So, you have come to this state via a number of state transitions. So, in between there are many states by which via input consumption we have come to this state. So, for the operation of the finite automata I do not need to remember this path, I do not need to remember this path, only remembering the current state is sufficient. So, that is the advantage that we have with finite automata. So, it can work with finite amount of memory and it needs to encode only the current state. So, a deterministic finite automata, it executes like this, it can take only one path through the state graph. So, it is completely determined by input. So, from one state, so there is no possibility that it can go to two different states on the same input symbol. So, it is its operation is determined by the input, whereas non-deterministic finite automata there is a choice. Like if there is a so it may so happen that some epsilon movements are defined, like from state say S1 there is a transition to state S2 which is marked as epsilon, and there is another transition marked on input A to the state S3. Now, if the current input symbol is say A, your input pointer is here and the current input symbol is A. Now, whether you make this transition or you do not consume the input and go to the you follow this epsilon path. So, that decision is non-deterministic in nature. So, whether to take epsilon move or whether to consume the input and go to the next state. So, that is a decision question. So, that is one problem, whether to take epsilon moves. Another point is if there are multiple transitions defined on a single input, like it may so happen that from state S1, so there is another transition defined. So, from S1 there is one epsilon move to state S2, there is a transition on A to state S3 and there is another transition on A to state S4. Now, the situation is more complex because now on the input symbol A, whether it should take epsilon transition or it should take the transition to state S3 or S4. So, that becomes non-deterministic. So, this non-deterministic automata, it can take some non-deterministic decision and can take any of these transitions. Now, whether whether this is valid or not, so that depends, like if there are some final states like this and then suppose these are the final states, and by taking this path maybe it can eventually reach this one, and by taking this path it can eventually reach here, and by taking this path it can eventually reach there. Now, when you have taken this path, whether you will reach this final state or not, that depends on the transitions that you have on this path and the inputs that you have on your input stream after this, after a whatever input symbols are available. So, if by that you can reach this one, then it is okay. Similarly, on getting this path, so if it is on A, you consume it, then the remaining part if it can be reached via these inputs, okay, by doing proper transitions, then that is also okay. Now, it is designed in such a fashion that both of them are not possible. So, it cannot be that by taking epsilon path and this remaining input you can reach here, as well as taking A and using remaining inputs you can reach here. So, if that is not there, if the automata is designed in such a fashion that only one of these final states can be reached by the next few input symbols, then you see that if you take a non-deterministic decision which is wrong, so that will not lead you to a final state, and in that case you can come back, you can follow the other path to see whether that can lead you to a final state or not. So, that way we can take a decision about this which path to follow, and by means of say backtracking and all, and this way we can have a automata operation. So, apparently it seems that this is a bit clumsy, but we will see that this is better in many cases, because the total number of states in the system may be less compared to a deterministic finite automata. So, we will see that after some time. So, this is an example, like an NFA can get into multiple states, like say this is the start state, as I was telling. On say getting 0, it can remain in this state or it can go here. However, on getting 1, it definitely remains on this state, but on getting 0, it can go to the next state or it can remain in the next state. So it is in this state. So, if the input is 1, then definitely it will make the transition like this. If the input is 0, we have a question. So, it can either go here or it can go there. So, if it get a 1 here, now you see that from this choice it can go to the final state, but from this choice it cannot go to the final state on getting 1. So, NFA will accept the string if it can get in a final state. So, this 101 is acceptable in this particular language because it can find a path by which it can reach a final state. Of course, in between it tried some other path, but that did not reach to the final state. So, they are not considered. So, NFA versus DFA. So, apparently as I said that it appears that DFAs are better, but NFAs and DFAs can recognize the same set of languages. So, whichever language is acceptable by an NFA, it is also acceptable by a DFA, and whichever language we can for whichever language we can construct a DFA, we can also construct an NFA. So, power wise both of them are equally powerful. So, both of them can accept same set of languages. However, as far as implementation is concerned, DFAs are easier to implement because we do not have any choice to consider. So, we have got only for every state we have got the transitions which are well defined. So, there is no choice to be considered. So, DFAs are easier to be implemented. So, that is there, but NFAs we have got choice. So, we have got difficulty in the implementation because it may need backtracking. However, it may so happen that NFAs may be simpler compared to DFA. Like here I have got an NFA where the language that we consider here is all strings that ends with 2 zeros. So, all binary strings ending with 2 zeros. So, this is the for this particular case we are trying to formulate the NFA and DFA. Now, you see this NFA, as long as there is 1, so it remains in this state. If it gets a 0, there is a choice, it can come to this state or it can remain here, but if it gets another, so if it get 2 zeros, it will go there. So, if I have a string like say 1 0 1 0 1 0 0, then getting the first one, so it will remain in this state because there is no choice, and the second 0 I have a choice. So, I can go like this or I can go like this. If I go like this and come to this state, then at the next time I get a 1, I find that this is the string becomes unacceptable. So, that was not a valid choice. So, we come back. Okay. So, input pointer is retracted and we come to this state, and so you take this transition now, and now after this if I get a 1, so it will remain here, then again 0. So, there is a choice between this path and this path. So, this way it can the NFA can operate. Okay. So, it can whenever it is finding that I cannot proceed further, it can retract the input pointer and it can come back to the previous state from where it can just try out a new option. Whereas, for DFA we do not have that thing. So, but the DFA structure is quite complex. So, as you can see from the diagram itself, so this also accepts the same language, that is all strings ending with at least 2 zeros. So, it is also accepting that, but the point is that this is in this case we have got the diagram is much more complex. So, DFA can be exponentially larger than NFA. So, this is the thing. So, here of course, the number of states in NFA and DFA are same, but so it does not have much difficulty, but if it will see some example later where we will see that the number of states in a DFA can be much larger than the larger than the number of states in the NFA. So, that is why for the representation of a regular expression, so it is better that we do it in terms of NFA, and while writing the corresponding recognizer, So, the program can be made recursive. So, it can try out the alternatives, it can backtrack and try out the other path like that. So, that way the recognizer can be made complex, but space wise. So, it will be saving the space because I do not need to have so many states, the number of states may be much less compared to the DFA. So, that is the general observation. So, regular expression to finite automata. So, we start with this lexical specification, and then from here we come to the regular expression. From the regular expression we convert it into NFA, and from NFA we convert it into DFA, and for DFA we have got table driven implementation of DFA. That is how this whole thing works. Okay. So, sometimes, so of course, it is possible that you do not make this NFA and go from regular expression directly to DFA. So, that is also possible, but normally it is not done. So, we follow the other avenue because there can be very well defined rule for converting regular expression to NFA. So, we will see some examples later. So, like so this is the so for say the NFA for regular expression A. So, for different type of regular expressions, so we can have it is like this. So, it has got the input for some regular expression A. So, it has got an input pointer and this is the final state. So, there will be a start state. So, for different types of A, I can have different type of regular expression. For example, if the regular expression A is only epsilon, then it is represented by the NFA where we have got this initial state, then this epsilon taking it to the final state. If the regular expression A is equal to this small a, it has got only the single character small a in it. So, it can go from this start state on this small a, it goes to the final state. So, this way I can define regular expressions for individual symbols that we have for the in the regular expression, whatever single symbols appear. So, I can make it like that. Now, if you are trying to if you have got two such NFAs constructed for the regular expression A and B, then you can join them together by, if the regular expression is say AB, then you can join them together by doing it like this. So, the final state of A, from the final state of A, put an epsilon transition to the initial state of B. Whereas, if the regular expression is A or B, so and you have already constructed the NFAs for this regular expression subparts A and B separately, then you can add a few extra states like so you take this these two extra states, okay, and add epsilon transitions. So, from the initial state, so you put an epsilon transition to the initial state of B, similarly put an epsilon transition to the initial state of A, and from the final state of B put an epsilon transition to the total final state of the whole expression. Similarly, from the final state of B put an epsilon transition to the final state. So, this way for A or B we can make the NFA. So, what I want to mean is that depending upon the regular expression, so you can construct it the small portions of it and then combine them together for getting the overall regular expression. So, this is another very interesting one for A star. So, I assume that I have already constructed the NFA for A. So, this is the NFA for A that is already constructed. So, this part is there. Now, for getting A star, I should have 0 or more occurrence of A. So, I take one initial state and a final state as extra and put an epsilon transition from the initial state to the final state. So, that way this is actually correspond to the 0 occurrence of A. Now, to make one occurrence, so you can go it like this, through an epsilon transition you come to A, make this A, and then there is an epsilon transition from the final state of A back to the initial state of the regular expression. So, you go back like this, then again by another epsilon you come to the final state. So, if you trace this diagram, then you can understand that this will realize the regular expression A star. Okay. So, this way we can convert regular expressions to NFA, and there is well defined rules like that for doing the conversion.